Assalamu alaikum. This is Mohammad Affan Khan, and today we are going to discuss beta stationary waves in a stretched string. Okay, beta, what we are going to do, we have tied this particular string, both ends of the string, to the ends of this ceiling. And what we are going to do, we are going to disturb this string in multiple ways. Like, what if I pluck this string? So what will happen? It will start oscillating to and fro like this, and this will make a loop. And there is a possibility if I pluck it a certain specific frequency, then what I will observe, it will start oscillating in two loops, like half part of the wave will be making crest and half part of the wave will be making trough, and that string will alternate its position, and then the trough will become the crest and the other half will become trough. And that is another possibility, that it can behave like this in three modes, like three loops it can form. Okay, so we will be discussing what is the basic criteria of different modes of vibration. Okay, so let's start with this first mode. This kind of pattern, or if you plug it at a particular frequency, this frequency is called as fundamental frequency, or we can call it first harmonics. Okay, what going to happen? I just plugged it, and I found that this particular string is moving in this position, like the like for half time it makes a crest, and for the half time it makes a trough. It is not like that it is making these are not two strings, this single string, but at one instance you can see the half part of it in the form of crest, and then for other half time you will see its trough, and then again it will alternate its pattern. Okay, G. So you can see that we have given this string a length L, okay, and we can clearly see that for half time, if it is making just crest or just trough, so this is not a complete wave. This is, you can say, a half wave. For example, while it's in this crest position, so you can draw a pattern like this to complete its wave. Okay, what I am going to try to do, I want to tell you that this is basically one complete lambda. All right, but since the length of the string is just L, not this part, this was just assumed, na? Okay, so we can say this particular length at this time is making half of wavelength. So we can write here that this length is basically equal to lambda upon 2. And since it is first harmonic, so let us put a subscript 1 here with lambda, that shows that first harmonics. Okay, so let's start. L is equals to lambda 1 upon 2, and what we need to do, we need to find the frequency at which it will initiate first harmonics. Okay, ji, beta, we know that V is equals to F lambda, and for first harmonics we can say that if we have first wavelength, the frequency will be 1 and velocity will remain constant overall. We can substitute the value of lambda here. We can write 2L is equals to lambda 1. So according to this, we may get 2L. And then the fundamental frequency or the first harmonics will be given as V upon 2L in velocity divided by twice of length. This is fundamental frequency. All right. Okay, now let's move towards the second part, which is second harmonics, you can say. This is called as the first one was fundamental frequency, na? So this is called as first overtone or second harmonics. What is meant by overtone? Overtone is the next, means the next frequency just after the fundamental. All right, now here you can see a different beautiful pattern that it says basically, like you can say, for part one we had to make this trough with this na, so we can see a full wave, but here we can see a full wave, and this is vibrating. These are not two strings. This is vibrating in a manner that half part of the string, that single string, is making crest and half part is making trough, and then they will change their positions. This trough will become crest and that crest will become trough. So this is vibrating in these two modes. Okay, now here, since the length is L and this is making a complete wavelength, so we can write L is equals to lambda 2 for this part, right? And we are going to find that what would be this particular frequency which will generate second harmonics. All right, so L is equals to lambda 2. All right, and again we start with our fundamental equation. V is equals to F2 lambda 2. Okay, let us put here lambda 2 is equals to L and F2 is equals to V upon L. But there is something interesting we can find. These two relations seems very different, like this V upon 2L, okay, V upon L. But beta, if we multiply and divide it by 2, so why? Just a moment. If we multiply it by 2 and divide by 2 as well, so we can write it V upon 2L. So what I did, I multiplied this 2 with L and left this 2 as it is. This is, yes, we have done this. This is equal to F1. So we can write here F2 is equals to 2 times of F1. And this is the second harmonics or first overtone, that if the first harmonic was generated at, let's say, 50 hertz, the second harmonics will be generated at 100 hertz. I hope you are getting. All right. Now let us move towards the third harmonics. All right, but the third harmonics, or you can say again, second overtone. Now system is vibrating in three modes. Third harmonics. All right, now here we can see there are two crest and one trough at a time, or for the other half cycle there will be two trough and one crest. Okay, so we can see better here that this is complete wavelength. And what is this? This could be half wavelength. Yes, we need to draw a crest to confirm it whether it is a complete wave or not. Okay, so we can write here this is half lambda. So the total length of the string, the same string which had length L, the total length now shows lambda plus half lambda. So you know, 1 lambda plus half lambda. And we can take LCM here. This would be 2 and 2 will be multiplied here. 2 lambda plus 1 lambda or just lambda. This will become 3 lambda by 2. And specifically we can write L is equals to 3 lambda 3 by 2. Why we are writing 3? Because this belongs to third harmonics. So lambda 3 will be equal to 2L upon 3 is equals to lambda. All right. Okay, now let us move towards that fundamental equation again, F3 lambda 3. Okay, let me tell you why V is not changing. We are taking V constant again and again. So why V is constant? Basically keep this in mind that V is change upon change of medium, and the medium has not changed. The medium is same. The length of that string is not changed. The material of the string is not changed. So V should remain same since the medium in which waves is vibrating is same. All right. Okay, so let us put lambda 3. Lambda 3 is 2L upon 3, and that would be 3V upon 2L is equals to F3, or I can write it here as well. 3V, 3 multiplied there on the left hand side, and the remaining part, which was the numerator 12, will be written in denominator. And now you can see that same pattern again. Let us separate this 3 from here. Yep, This is something we have already uh, seen. This was F1. So F3 is equals to 3 times F1. Wow, now we can see the pattern clearly, that the first harmonics will be something V upon 12, but the second harmonics will be twice of the frequency of first harmonic. The frequency of third harmonics will be the thrice of frequency of first harmonics. And can you tell me something about the fourth harmonics? Let's make a side note here. Fourth harmonics will be F4 is equals to 4F1. F5 is equals to 5F1. So in general, we can write here what would be the frequency of nth harmonic, like first, second, third, fourth, fifth, any number. That would be nf1. If f4 is equals to 4f1, f5 is equals to 5f1, then fn must be equal to nf1. And we can say where n is equals to 1, 2, 3, 4, and so on. All right, I hope you are getting the idea. Few things we need to keep in mind, that these points, point of zero amplitude is called as node. These are two nodes. And the point of maximum amplitude is called antinode. Okay, so can you tell me that how many nodes are here? Yes, sir, there are one, two, three. The point of zero amplitudes are nodes. So this is a node, another node, and another node. And how many antinodes are here? There are two antinodes. First is here, and the other one is here. Similarly, for this part, we can write this one is node, this one is node, and again node. And this is antinode, antinode, antinode. One interesting thing more we can see here, that since this string is tied from both ends, na, so it cannot vibrate here. So what you can say, for a closed string, for string closed at both ends, string tied at both ends will always form nodes in the end. You can see the pattern overall. Or if you can make four harmonics or five harmonics, you will always find nodes at the end, because string is tied from this place, na? So we will observe always nodes from on the close end. These are called close ends. Okay, I hope this is clear to you. Now let's move towards some exercise or assessment part. Okay, beta, they are saying, if the fundamental frequency means first harmonics of a guitar string is 220 hertz, the frequency of second harmonic is, so that is not a problem for us. We know that f2 is equals to 2f1. Wait a minute, is guitar string a closed string bound at both ends? Yes, sir. The guitar strings, let us consider this as a guitar. All right, so strings are closed at this place and at this place. So string is bound from both ends, so we'll always observe nodes at the both end. So this is same problem which we have discussed above. All right, so let us put its value to, we do not need to see the options now, because we know how to solve it. Okay, so this is 2 multiplied 220, and that would be 440. Two zeros are 0, two twos are 4, two twos are 4. So this is 440 hertz. Yes, C is our answer, teacher. All right, very well done. Okay, then next, let's move towards the second question. The distance between a consecutive node and antinode is, oh, this is something a bit tricky. Okay, no problem. Let us draw it. Let's say we are observing standing wave here, And let us consider fourth harmonic, no issue. Okay, this one is a node, this is an antinode, and this one is again node. Okay, we need to find the distance between a node and antinode, the consecutive node and antinode. All right, what would be the distance? No problem. Let us break this, let us decode it. But how much wavelength is this? Okay, how much wavelength is this? This is lambda, sir. And what about this? This is lambda by 2. This is half wavelength, na? This part. And now we need to do another half of it. A node with another node makes half of wavelength. But what about the node and antinode? We need to half it again. So that would be, yes, lambda by 2 ka bhi half. So that would be lambda by 4. Yes. Wow. So we can say the distance between a consecutive node and antinode is lambda by 4. We can see it here as well. This is antinode, this is again node, an antinode, and a node again. This is a node as well. So here it is. This is complete wavelength. And can you tell me how many nodes need to complete a wavelength? So this is complete wavelength. First, 1, 2, 3. 3 nodes will make a complete wavelength, and same goes for antinode as well. All right. What about this? So this is half wavelength. And what about these 2 points? So this is half of half lambda, half of half lambda. Okay, what we did, this was lambda, we did it half, and then again half. So half of half lambda, yes, that would be 1 upon 4 lambda, or lambda by 4. So our answer is correct. I hope this is clear to you. Okay, last question. By what factor would you have to multiply the tension and stress string so as to double the wave speed? This does not seem relevant, but this is relevant. But we know that velocity of wave in a medium is tension upon linear mass density. All right. And what we need to do, we need 2 times of velocity. So yeah, we need to make velocity 2 times. So what we will do, we can write this equation as, let us do this complete problem. V square is equals to T upon mu. What I did, I took square on both sides. All right, so V square mu is equal to T, and we need to find this particular tension, that what would be tension if the velocity become double. So beta T is equals to mu V square. All right, and we want to do twice of velocity, so the tension would change. So I am putting here a dash here. So this was T, and the new is T dash. Okay, G. The square of 2 will be 4 4V squared. Okay, let us separate this 4. We can write mu V square. Can you tell me what was mu V square? No, sir. I guess yes. Mu V square was previous tension, the old tension, na? So we can write 4 times of T. We can write T against mu V square. So this gives the answer that if we increase tension 4 times, then the velocity will be doubled. So I hope this is clear to you. This was all from my side. I hope you must have enjoyed this lecture, and I believe that I have completed almost all the parts required for this topic. Thank you. Allah Hafiz.